Can you make this higher?
No, yeah, I don't know. I think this is as high as it goes. Yeah.
If I zoom up, then
It's a bit too, yeah. It should tell you.
After the lecture this morning, I stick to the schedule. And it's my pleasure to announce Glynn Winskel for the first talk, the first afternoon session on quantum event structures. Okay, and it's my pleasure to be here. Congratulations, Samson. First met Samson in America, at least was aware of Samson. I had in 82 in Barcelona. We started talking, and as you do when you're talking, we started walking. And we walked quite far. And then we suddenly realized we both had a terrible sense of direction, and we didn't know where the hell we were. And somehow we recovered the situation, we're here today. But I really don't know how we found that. But in fact, before I met Samson, I knew his wife Ross, through mathematics and also from the bar of Wilson Court, and I came out close to Girton College, and she used to serve at the bar, and I used to drink there. And I thought, so maybe in memory of those old days, I crawled around in the cellar of Emmanuel and found this. Actually, we're older than this, but there's a kind of Dorian Gray effect here. Shockingly old. Looks at this. Okay, but I'm very pleased to be able to talk about something that both Prakash and Samson helped me out with at a dad school recently. I've been working on and off, thinking about things like event structures and how to cope with quantum features with event structures, and got kind of a bit stuck because I got sidetracked by the consistent histories approach. And what happened was, we're talking to Prakash and Samson, I kind of basically pushed that away, and it's got some results. So I'm pleased to be able to talk about it today. Some of the things are a little bit preliminary, but I hope you get the idea. I'm going to start out with a brief introduction to probabilistic event structures, and then show that that certain quantum event structures give rise, at least locally, to probabilistic event structures. And then very, very briefly indeed, I'll talk about quantum games and quantum strategies and how they suggest the language of types and operations. Okay, sorry. Event structures. I have to say very quickly what they are. They're a way of looking at computation in terms of the event occurrences the computation can do. And the events are related by a causal dependency relation, which is a binary relation, saying, for example, in this situation here, that in order for E to occur, it requires the prior occurrence of E prime. And then in order to have non-determinism, one has a consistency relation, picking out those sets of events that can occur together. And then there's some kind of traditional axioms that are put on these things. Kind of like it. But the one important relation is that one has an explicit notion of concurrency of events in event structures. Events are concurrent, they occur together somehow independently, and what that means is that they are both consistent one with another, and moreover, neither one is causally dependent on the other. Once you've got this kind of, if you've got that intuition about an event structure, then if you've seen an event E and it depends on previous events, then you should have been attentive, you should have seen the previous events. So you get a notion of state by picking out those subsets of events which could occur together at some stage. They should be downwards closed because of the last remark, and they should also be consistent. And so you get configuration, possibly infinite, which forms a, when you order it by inclusion, forms a very simple time stop domain. And I'll use this for all of the configurations, fine as an infinite. For this, the final ones, I'll use this notation. Okay, so how does one add probability to such structures? People are used to putting probability on trees, and here we're putting probability on a much more subtle kind of structure. But there are ideas from domain theory that we can borrow here and just take as a definition, not a particularly workable definition, but we'll come to address that in a moment. structure, put it like this, a bit cut off there, oops, which is together with a normalized continuous valuation on its Scott domain. And what that means is that there's an assignment of a value between, in the interval 0 and 1, to the open sets. So here you have the domain of event structure, domains of configurations of event structure here. Here's a Scott open set, and what that means for it to be Scott open is that it's upwards closed, and its boundary consists of just finite configurations. And what this continuous valuation does, it gives you a probability of a result being in this open set. So that's the intuition. And so it satisfies reasonable axioms. Probability being anywhere at all should be 1, probability being the empty open set is 0, of course. And if you make your open set smaller, then you decrease the probability. And then there's this kind of modularity condition that says if you look at the probability of being in the union of two open sets, because of the overlap in the middle, it's not just the sum of the probabilities of being in the components, but you've also got to subtract the probability of being in the intersection. And then what makes this a continuous valuation is that if the open set is given as a directed union, then the valuation is just given by the sum of that directed union. Now this is a kind of reasonable as a definition, but you can see that we have this structure of event structures, we have configurations there, and we have then this valuation, continuous valuation on the open sets, and it's not hugging the structure of the configurations very closely, is it? So what we're going to do is give a characterization in terms of something more workable. Oh, okay. Sorry, something getting cut off here. This is showing. I don't know if anyone can adjust this for me. This is giving you the full slide. That's not. So here's the workable characterization. So a probabilistic event structure. So what we do is we just you can characterize. So first of all, if you have a continuous valuation, then a very special kind of open set will be one in which you just take a finite configuration and you just look at all of the configurations which dominate it. Okay? So what will happen is a continuous valuation will give rise to a value associated with that cheese subtended by a finite configuration. So it's giving you a value associated with every finite configuration. But what conditions are associated with that assignment of values to finite configurations are necessarily sufficient in order to get exactly, to be able to recover exactly continuous valuations? And that's what this slide is about here. Well, thanks very much, by the way. Correct. So and what this slide is saying, that well, it's sufficient to insist that the following conditions hold. That the valuation associated with the empty configuration is 1. And then that these so-called drop functions are always non-negative. But what are they about? Well, think of a particular open set subtended by y, finite configuration y, and then think about x1 up to xn, which are configurations above y. And what these drops are concerned with is giving a probability to the shaded area here. Okay? So it's the probability of being above y and not being above one of the x1 up to xn's. And these drop functions satisfy lots of nice mathematical properties. They can be given in a kind by recurrence relation and so on. But ultimately, what they're saying is, because of the inclusion-exclusion principle, what they're saying is they're just giving you the probability of this value. Yeah, but you can express it. You can express it in this way. See, using the fact that the intersections here can be given by unions, correspond to unions of configurations here. So if you're looking at all the things which are above x1 and x2, they're all the things which are above x1 union x2. Using that fact, we can express these drop functions in this way. We look at the value associated with y minus the value of being in this bit here. Okay? And we insist that that's non-negative. And that condition does hug the structure of configurations quite closely. And in fact, even more than that, you can show that if you insist on this condition holding, you don't need to insist on this condition holding in general, it's sufficient to insist that it holds for just these covering intervals of this form, where in other words, x1 up to xn are above y, and there's nothing in between. And these covering intervals correspond very closely to occurrences of events, and so one is getting something that turns out to be a much more workable definition of a probabilistic event structure. Okay, so by standing on the shoulders of giants, one can then go from here and say if you have such a probabilistic event structure presented in this way with these drop functions, then it will give rise to continuous valuation, and that continuous valuation will be associated with a unique measure on the Borel subsets of configurations. So that's a very quick introduction to probabilistic event structures, but let's just look at an example. Here we're looking at the configurations associated with a very simple event structure. We've just got two events, A and B, which are concurrent with each other. So the configurations look like this. You can either not have seen any events at all. You can see A, B alone, or you might see A and B together. And configuration valuation is saying probability of seeing the empty set or more than the empty set is 1. Probability of seeing A, either singleton A or anything above it, is a half. Similarly, this probability of seeing B is a quarter, and probability of seeing A and B together is a quarter. Now from this, we can derive the probability of being at a particular, ending up with a result which is at a particular configuration. So for example, let's look at this guy here. What's the probability of being here? Well, the probability of being above here is a quarter, and there's nowhere else to go, so the probability of ending up exactly here is exactly a quarter. What about here? The probability of being above A is a half, and but of course we might be above A and also have seen B. So probability of ending up with exactly this configuration is a half minus a quarter, namely a quarter. What about the probability of this guy here? Well, it's the probability of being above B and of ending up exactly here. It's the probability of being above B and not having seen A. So it's a quarter minus a quarter. So there's probability 0 of ending up here. So this is a configuration which you can think of as a configuration that's going to occur at some point in the configuration. It may occur at some point in the computation, but it's somehow transient on the way to a larger configuration. And if you want to know what the probability is of ending up at the empty configuration, well, you look at the drop associated with the interval starting here and ending here and here. So what's that? That's 1 minus a half minus a quarter plus a quarter, which is a half. So, quantum event structures. So this idea has been around in my head for a while now, but only at the Dijkstoel summit did I manage to get a theorem associated with it. The idea is that you take an event structure and you think of the events as being events of elementary measurement or as being preparation events. So we're going to take an event structure and then we're going to associate with each event an operation which might either be a projection on a Hilbert space or a unitary operation. Okay? And we're going to do that in such a way that if the two events are concurrent but not independent, then the associated operators commute. So via this bracket notation, that's just saying the two operators commute. going to assume some initial state of this quantum event structure, which will be given by a density operator. In a particular case, that would be a pure state, of course. And the idea is, if you think of a configuration, it's probably easier to just think of a single configuration first, is to think of a single configuration as a kind of distributed experiment. See, the individual configuration W inherits the partial order from the ambient event structure, and that's saying what kind of measurements can be done somehow independently of others, what measurements depend on others, and so on. And you can think of this as being some kind of distributed experiment where that independence might be reflected by the fact that the measurements are actually occurring, measurements or preparation events are occurring somehow far away from each other. I think we've already said that a projector is of course a kind of associated with an elementary positive test, and if you think of the unitaries as kind of preparation actions. Okay. Which you might think of as preparation actions might be, for example, changing the basis, or they might be waiting for some period of time, letting the system evolve in some way. Okay. Now, associated with an interval going from one configuration to another, one finite configuration to another, we can take a covering chain from, say, the start of the interval to the end of the interval. And, of course, that gives us a chain of operators. And we can compose those operators together and get ourselves an operator associated with the interval x to y. And it doesn't matter what choice we make of the covering chain, because we're associating concurrent events with commuting operators. And there's a little result there about Masakevich trace equivalence, which is justifying the fact that we get a unique value in this. And in particular, associated with a finite configuration, we can look at the operator associated with the interval starting off at the empty configuration. Alright. So once now we have a start state, we have this initial density operator, and what we can do is we can look at the effect of performing those events in X as an operator on that density operator, and it gives us a subdensity operator where the trace may be less than or equal to 1. And in particular, if this density operator was a pure state, what this would just be take the initial that pure state, act on it by the operator, and then take the norm squared. Okay, that's what we would be. Okay, and so that's the operator, and then we can get a value from it, and the value we get is just by getting the trace of that. And what I should have said, and the trace that trace here is, in the case where this is a pure state, would just be the norm squared of the operator acting on that pure state. So we've got something that looks like a probability measure associated with each finite configuration. Or sorry, we've got something that looks like a probability, or something like a configuration valuation associated with each configuration. But it isn't quite that, but it is almost that. The fact is that if you look at a particular configuration, and you think of this as an experiment, then you've got this kind of subdomain of all of the subconfigurations. And on that, you can show that that is a probabilistic event structure. In that V that we got, that valuation that we got, does restrict to give us a configuration valuation. Okay. So we have associated with an experiment, we have on the possible results, we have a probability measure given in this way. And if you like, you can think of this as a kind of a new take on the consistent histories approach to understanding quantum mechanics, but without the traditional deep coherence conditions, which actually don't seem to be right, in the sense that they're very sensitive to the, they work with histories which are just sequences, and their deep coherence conditions are very sensitive to the beginning and ends of those sequences. And this is where the suggestion of Samson and Prakash was very handy. This basically gave me the confidence to forget about that traditional approach and concentrate just on commutation. So here, the traditional deep coherence conditions, traditional to consistent history approach to quantum theory, are being replaced by something that's somehow in the spirit of traditional quantum theory, and it's just really technically just compatibility with respect to the domain theoretic order. Okay. So, rushes a bit. You might think, well, okay, a lot of this was to do with particular configurations W. Why didn't I just restrict attention to those right from the start? Why did I look at what one could think of as non-deterministic quantum experiments rather than just, if you like, some kind of deterministic quantum experiments? Well, the reason is that I want to put probability on top of those experiments that you can do. That's sometimes just a feature of the physical reality. If you have experiments that are going on far away from each other, there's no way you can necessarily coordinate things. You have to do things probabilistically. And so now we have, because we started with a non-deterministic quantum experiment, we can overlay probability on that and get a probabilistic quantum experiment. So we start out with a quantum event structure, and then we're going to put probability on that, so assign probability to the different experiments you can do here by having a probabilistic event structure which related to the quantum event structure by a total map of event structures. So this is something which takes configurations of P to configurations of E in such a way that it's locally injected on events. That's the right thing to do, of course requires some argument, but I can't give it here. So that's what a probabilistic event structure is. It's like a quantum event structure with this overlay of a probability put on top of the experiment you can do in the quantum event structure. And of course, what this means is we can, if we have such a probabilistic event structure, we can look at if we have a Borel subset of the configurations of the quantum event structure, then we can look at the probability of getting a result within that Borel subset. And express it as this Lebesgue integral here. See, by virtue of this map and the fact that P is a probabilistic event structure, we get a measure on E, which is ranging over the experiments you can do, and that's this measure here, mu f minus 1. And then, given a particular experiment W, this is the probability of having a result which is a subconfiguration of W, which is in this thing L. And of course, this L could be described by a little logic, the Borel logic for events. And so, I won't go into the details of this, but this is the kind of thing you can do. I'm not sure how stable this is, but it's a reasonable thing to do. One just has basic propositions saying an event has occurred. One has quantification over events. That's okay, provided your event structure is accountable. And one can, through this kind of logic here, express the kinds of things that you want to express, say, with EPR experiments or Bell experiments and so on. You could express, for example, the anti-correlation between the spin of two particles in this kind of way. Well, so how can we turn this into some kind of language? And here I've not got the full story yet, but the first idea is to move to quantum strategies. So we move to quantum games. We'll take a quantum game to just comprise a quantum event structure with an initial state, so given by some density operator, but where in addition addition, the events are associated with polarities, player or opponent, to specify whose moves those events of the quantum event structure are associated. And then a quantum strategy is going to be a probabilistic strategy on this quantum game. What does that mean? Well, I have to be quite quick here. That means it's a strategy, and there's a lot to be said here about what this means, but roughly what it means is this is a total map going from an event structure S to A, which is such that it's receptive. Anything that the game says the opponent can do is somehow seen in S. And moreover, it's such that the only extra causal connections that can be made in the strategy are ones that are going from causal connections going from making dependencies on opponent moves to player moves. But then, of course, then we need this S that itself be a probabilistic structure, so we have a configuration valuation on that to make it such. However, of course, here we've got player moves and we've got opponent moves, and the opponent moves we have no control of the probability there. So again, I'm being a little brief here. Probabilistic event structures here have got to be such, in order to account for that, have got to be such that they're only probabilistic event structures when you project to the player part. Okay, being a little vague. Then what you find is if you play a strategy against a counter strategy, you can do that by pullback. What you find is you end up with, as a result, a probabilistic experiment. So the effect of a play and a counter play against each other is a probabilistic experiment, which you can then think of having certain probabilities of ending you up in certain states, given by those Borel conditions there. Okay, but the bit I'd like to bounce off Prakash and Samson, and I know this is being incredibly quick, is that one can now take the structure of concurrent games and concurrent strategies and pretty much extend it pretty directly to quantum games. One has a simple parallel composition of games. It just means putting games side by side. One could do the same thing with these quantum games. You just have to be careful that you extend the Hilbert spaces appropriately and extend the assignments of events to operators appropriately too. Of course, give the appropriate initial state, but that's reasonable enough. And you need to do something similar for the dual game. All of that goes through. So it's giving us, it's not being explored very much, but it's giving us, by virtue of that structure being a model of affine linear logic, it's giving us an affine lambda calculus of quantum strategies. How expressive it is and how useful it is, I don't yet know, but surely there's a lot of potential here. But there's something that's bothering me, and this is the question to these two chaps here. Once you're at liberty to choose for your ground types the initial state that you want. So you can put as much entanglement in there as you'd like. But if you just kind of follow this scheme here, you're not able to introduce new entanglement. So what it's suggesting is that there's an extra type operator which allows you to introduce extra entanglement. What is it, guys? Thank you.
Questions, remarks? Anybody? Yeah.
Well, you could consider having a compact structure. That look. I don't know.
Standing here, no. I'll think about it.
Part of the vector structure.
Yeah. What I thought was some creation and annihilation, things like that.
Well, but the
that's
unit
a heavy
of
stuff.
the compact
What space?
structure is will behave like that.
I see. Yes.
Basically, it should give you a belt state.
We're going to have time over the next few days. I'll have that one soon.
I want to deflect your question by asking another question. So, I don't know if you are familiar with Raphael Sorkin's work on quantum measure theory,
Not very familiar.
which is refinement of the notion of consistent histories, which I realize you've departed from, not your knowledge. But there are some interesting ideas there. And so what he did was he took the consistent histories approach and formulated it as a kind of measure theory. With a slightly different axiomatization of what measure means. And he calls these things quantum measures. And even though you're not following consistent histories, you might well be able to do an interesting analogous thing. And there are interesting predictions he made based on that about 3-slit experiments versus 2-slit experiments showing potentially new features. So these are interesting things we need to explore. And simple, not complicated.
Simple, yes.
Can you go back to the definition of a quantum structure? Right here. So you have this condition and your concurrency imply the connectivity. And if you have two operator that they commute, then you can do the simultaneous diagonalization. Then quantum effect disappear because you can choose appropriate the basics, and then it became classical things.
Everything is, yes, but of course not everything is commuting here. This is just saying that for commuting events, for concurrent events, they have to commute. It's allowing, of course, there's an extreme case where there are no concurrent events. We just have a sequence of observations, and then there would
So
be.
you cannot,
Then there would be quantum effects.
you cannot remove this condition.
No, well, not the way. No, I think otherwise everything would not work. But
Very necessary.
yes, it's necessary. Yes.
Feature.
Yeah. Thanks.
Anybody else? Yes.
Another comment is that I think this could be, that what you've described here could be a nice setting for looking at, it depends of course how, I think the causal ordering is presumably, if you think of some combination of quantum experiments happening in, at least in something which is a sort of trace of space-time where you have some causal structure, I think there are a lot of very natural questions that arise there. And,
Yes,
this could be a setting for that.
yes, yes. The kind of causality you see in space-time is not quite the same as the one here, of course. But it's very. When one wants to talk about imperfect information games, what you do is you restrict strategies so they can't see. You can access relations, and it's like an access relation. It's basically saying that at a certain time causal dependency is just not allowed. And so that's my view of
So there might be some refinement of this setting that allows you to take account of it seems to me
yes, and I think it's taking us in the direction of imperfect information games associated with an access relation which comes from the space-time.
So my article in your festival is about the difference between causal structure in space-time and in computation.
Yes.
I probably read it.
So I guess let's thank the speaker again. And